Okay, so let's start it. Today's the community the topic of the community meeting, it's about the safety of implementing the joint consensus in CURP algorithm. And and let's talk about the safety about the joint consensus in the CURP algorithm. So let's talk about the background first. And in our first community meeting, we introduced the Xline membership change implementation mechanism that the change one node at one time. And since we already have implemented the single step membership change, so why do we need to implement the joint consensus? So let's take a look at the likeliness issues which is caused by the this change one node at one time mechanism. So assuming that there are three nodes like A, B, C, and they are deployed in the three different data centers. And now we want to change the configuration from ABC to BCD so we need to add the node D first into the current cluster first, and change the configuration from ABC to ABCD. And then we remove the node A and to get the final configuration BCD. And during this process, if a network partition occurs, like to separate it, split the network into two parts, like the AD and BC, then our cluster will be unable to elect a leader. The reason for these issues is that during the single step change process and the cluster configuration go through the following stage. It will first be the ABC and then to the ABCD and finally the BCD. And when the cluster enters the intermediate configuration ABCD, the quorum size needs to be greater than 3. And leading to cluster unavailability during the network partitions. And if we use the joint consensus, the cluster configuration go through the following stages from ABC to the joint configuration. Here it's the ABC and BCD, and finally to the BCD, where this ABC and BCD represents the joint configuration. So let the QC denote the possible quorum set of the configuration C. Then we will then we got the Q ABC like AB, AC, and BC. This is all the majority nodes in the current cluster, in the current configuration ABC. And also we have the QBCD like equals BC, BD, and CD. So for the joint configuration, we have the Q joint QABC and BCD will be the Cartesian product of QABC and BCD. It will be the AB and BC means ABC, and AB and BD means ABD. And X delta, we will have the ABC, ABD, ABCD, ACD, BC, and BCD. And clearly, even if a network partition occurs when the cluster is in the intermediate state, the cluster can still reach the consensus through the BC, which is one of the quorum state of the cluster. So let's talk about the so that's why we want to change the our membership change mechanism from the single step membership change to the joint consensus membership change. So let's talk about how the safeties of the backend and the front end of the CURP protocol. So let's talk about the definitions. So the first one is the configuration. So as we all know that during the joint consensus configuration change process, there will only be two types of configurations. The uniform configuration, which is a CI, which is the ABC in here, which is the configuration ABC in the liveness cases, and the joint configurations, the CI and CJ. And the uniform configuration CI can be considered as a separated a special type of joint configuration, especially CI and CI, especially the joint configuration of CI and CI, right? And here is the quorum definition and the backend commit. So let's denote by the QCI the set of the all valid majorities under configuration CI. And for example, for CI equals to ABC, 3-node configuration, and we can have the QCI equals to AB, AC, BC, and ABC, which means all the possible quorum in the under the configuration ABC. So for the joint configuration, CI/CJ equals to ABC and ABD, and we will have the quorum set of the joint configuration, like which is the Cartesian product of the CI and CJ, which is AB, ABD, ABC, ACD, BCD, and ABCD, and clearly the CI it's equal to the quorum of the CI configuration is also satisfy the condition we mentioned above. So let's denote the set of the nodes that has successfully replicated the log entry LE by R. The R means the replicated nodes. So if the nodes that we have already replicate the our log entries to these nodes, it means the R belongs to the QCI that we will say that this log entry has completely complete backend commit, also known as the slow commit on CI configuration. And here we'll have some invariant to ensure that this joint configuration will work properly. And the first one is the it's about a configuration change. And we know that at any stage during the configuration change process, any two agent configurations, CX and CY, will satisfy that for all P belongs to QCX, and for all Q belongs to QCY, and their intersection should not be emptied, must not be emptied. And at any given time, there will be at most one uncommitted configuration in the cluster. And in other words, the next configuration can only be proposed once the current configuration has been committed. Here, this is two configuration that to make sure that the cluster during the configuration change process won't be bothered with the the brain split issues. And we also have some invariant about the leader election. That is if a proposal P has been committed, regardless of fast committed or slow committed, any newly elected leader will not lose P. And the follower, and also we have a follower will vote for a candidate only if the last term of the follower is less than the last term of the candidate, or the last index of the follower's log is less than or equal to the last index, the last log index of the candidate when the last term of the follower is equal to the last last term of candidates. So a follower will vote for the candidates only if this condition is satisfied. And this two invariants was to describe the safety requirement of the distributed consensus. So let's take a look at the membership change configuration. So the cluster configuration change steps will including 6 steps, which can be separated as 2 phrases. So we will refer to the step 1 to 3 as the phases 1, and the step 4 to 6 as phrase 2. So the first step is that a client A will initiate or configuration change request. It want to change the current cluster configuration from C1 to C2 to the leader, and the next steps, when upon the leader receiving the configuration change request, the leader will generate the joint configuration C1 C2 and then write this configuration into its O log, and then switch to the configuration from C1 to C1 C2 to the joint configuration. And then the leader will send append entries request to all the followers to append this C1 C2 to their logs. Once a follower has appended CIC2, has appended this joint configurations log, and it will immediately switch their old configuration from the uniform config C1 to the joint configuration C1 C2. And after confirming, so from now on, we have done the phrase 1 of the cluster configuration change process, and then we will go in the phrase 2 of the configuration change. So after confirming that the C1 and C2 has been committed, the leader generates a new configuration C2, and writes this new configuration C2 to its O log, and then switch its configuration from the joint configuration C1 C2 to the uniform configuration C2. And then the leader will send an append entries to all the followers to append the C2 to their logs. Once a follower has appended uniform configuration C2, it will immediately switch its old configuration from joint configuration C1 C2 to uniform configuration C2. And after confirming that the commit of C2, the leader will check itself, will checks if itself belongs to C2. If yes, and then the configuration change is complete. And if not, the leader will step down and an election will initiated by the nodes in C2. And due to the requirements of the 2-phrase commits, of the configuration change, the immediate state will an immediate state may occur if the leader crashes while switching the configuration from joint configuration C1, C2 to C2. And in this case, the cluster configurations remains in C1, C2. And for its of description, we refers to the step 1 to 3 as the phrase 1, and step 4 to 6 as the phrase 2. And in such a situation, we have two solutions. The first one is that a client will retry after a timeout and send a configuration and resend the configuration change request to switch the cluster configuration from C1 to C2 to the new leader. And the new leader, upon receiving the request, generates the new configuration C2 and completes the previously incomplete change operation. And the second one is the client B will sends a configuration change request, which means to change the cluster configuration from C1 to C3 to the new leader. And the new leader, upon receiving the request, will generate the joint configuration C1, C3 and switches its configuration from C1, C2 to C1, C3, and thereby initiating a new round of reconfiguration. So this is the membership change process of the backend in the CURP protocol. And as we all know that there are two different passes in the CURP protocol, which is the fast pass and the slow pass, or the front end and back end. So the joint consensus, it's the joint consensus, the safeness of the joint consensus has been proved in the RAFT protocol, but it may not be as right in the CURP protocol, because the protocol has the front end. So if we implement the joint consensus, mechanism in the CURP protocol, that what safety issues will happen in the front end. So let's take a look in two cases. And in the case 1, assuming that there are 4 nodes like A, B, C, D forming a cluster, and with A being the leader. Now we change the configuration from C1 ABCD to the ABCD EF. At the time T0, A writes the joint configuration C1, C2 to its local log, and then switch its configuration from C1 to C1, C2. And at the time T1, and a client will make a proposal P under the configuration C1 and receive a successful response from the A, B, and C satisfying the super quorum. And therefore, we know that the proposal P is fast committed. And at the time T2, the configuration C1, C2 is committed to the cluster. And at time T3, the leader A crashes. And at the time 4, B becomes the new leader. And since the configuration C1, C2 was committed at time 2, so the configurations on B must be C1, C2. And at this point, the cluster have A nodes requiring P to have at least 3 replicates to be recoverable. However, P is only safe on B and C in the cluster, so P cannot be recovered. leading to the loss of the already fast committed proposal. So the main reason of this problem is that in the CURP protocol, the clients need to know the current cluster configuration. During the configuration change process, the cluster can have at most 2 configurations simultaneously, 1 committed configuration and 1 effective but uncommitted configuration. A newly elected leader might use an incorrect configuration for recovery, so it will leading to the loss of the fast commit proposals. To address these issues, we need to impose the following constraints on the fast commit proposals in the CURP protocol to ensure that the client cannot complete a fast commit with a configuration inconsistent with the majority of nodes in the cluster. The specific constraints are as follow. The first one is that only when the client receives the successful responses from the superquorum of the CI configurations, which includes the leader execution result of the proposal P, can the client consider that the P has achieved a fast commit under the configuration CI. And the second is that any node in the cluster, be it leader or follower, must now return a successful fast commit response to a client whose configuration is inconsistent with its own. So by adding this, by imposing this constraints on the CURP protocol, we can make sure that the client won't achieve the fast commit when its configuration is inconsistent with the leader or other nodes in the cluster. So let's take a look in the case 2, that the same 4 nodes A, B, C, D with A as the leader exhibit a situation that can lead to the loss of fast commit proposals during the phase 1 of configuration change process. At the time T0, the leader A writes configuration C1, C2 to its local logs and switches its configuration from C1 to C2. And at the time 1, and then the leader crashes before performing the append entries to on other nodes. And at the time 2, the B is elected as a new leader. And then the configuration of nodes B, C, D are all C1 because they don't receive the append entries from the from A, which is crashed at time 1. And at time 3, a client proposes proposal P to the cluster using the C1 configuration. And as we can see that the proposal P is saved to the superlative pools of B, C, and D. And while the B is the leader, and it will return the execute result of the proposal. So we know that a P is achieving the fast commit. And at the time 5, the B crashes before performing the append entries to other nodes. And A has become to the leader again. And since A's configurations, it's C1 and C2. So the cluster will now have A nodes requiring P to exist at least 3 replicates to be recovered. At this time, P is only safe in the B and C, so P cannot be recovered, leading the loss of an already committed proposal. So the root cause of this problem is that a client proposed P using the committed configuration C1, while the newly elected leader has the current configuration C1 and C2, and it is naturally impossible to recover a fast commit proposal under C1 using the C1, C2 configuration. So it seems that if we always choose the committed configuration for recovery, such issues can be easily resolved. But is this really the case? Let's examine other scenarios. Assuming that the current cluster is in phase 2 of the configuration change process. So at the time 0, that the leader A writes configuration C2 to its local log and switches configuration from joint configuration to the uniform configuration C2. And at time 1, the leader A successfully replicates its configuration C2 to M nodes in the cluster where M is larger than or equal to the superquorum. Then at the time 2, a client proposes a proposal A, a P, using configuration C2. And P is safe on the superquorum nodes. So it will achieve the fast commit. And at the time T3, the leader A crashes, and the node B wins the election to become the leader, to become the new leader. And since the node B is unaware that the A has replicated the C2 to a quorum of nodes, it does not know that the C2 has been committed. Therefore, the node B will use the already committed configuration C1 and C2 to perform recovery. So which result in the loss of the fast commit proposal P under configuration C2. So why does this happen? The root cause of these issues lies in the CURP algorithm, where a configuration CJ being the committed has two implications. The first one is the configuration CJ has been replicated to a quorum of nodes in the cluster. And the second two is a quorum of the followers in the cluster is explicitly aware that CJ has been copied to a quorum of nodes in the cluster. And for clients to fast commit a proposal P under configuration CJ, and it only requires that CJ be copied to a superquorum of nodes and that the leader returns a successful response for the common execution. When the leader crashes, the newly elected leader might not know that the CJ has been committed and may therefore choose the incorrect configuration CI-CJ for a recovery, leading to the loss of proposal P. So to resolve these two issues, we must expand the definition of superquorum and the recovery quorum in the CURP protocol to accommodate the requirements of joint configurations. So let's take a look at the new definitions. So the first one is the superquorum and the from end commit. We can use SCI to devote all the valid superquorum sets under configuration CI. And for a joint configuration, CI-CJ means all the valid superquorum sets under CI-CJ are given by SC. The joint configurations superquorum is equal to the Cartesian products of SCI and SCJ. So when a client proposes a proposal P to the cluster, if the following conditions are met, the first one is the client receives the executed result of P from the leader, and let R denote the set of all nodes from which the client has received successful responses, and R belongs to SCI. then the proposal P is considered to have achieved from N commit, also known as fast commit under configuration CI. And the recovery quorum combining the definition of the super quorum mentioned above, we can derive the definition of recovery quorum. And we can use the RCI to represent all the recover quorum set under configuration CI. And then for all valid recovery quorum set under configuration CJ, and we can have this replication quorum of the joint configuration CI/CJ is equal to the Carcino products of RCI and RCJ. So during the recovery process, if proposal's replicates node sets R/P satisfied these conditions, and we will say that the proposal P can be recovered. And for proposal that have been fast committed, the newly elected leader needs to recover them, and the recovery process must satisfy the following two guarantees. The first one is for proposals that have already been fast committed, they must be recoverable on the newly elected leader. And during the recovery process of P, any conflict proposals must be prevented from being recovered. So how does this definition of recovery quorum and super quorum meets the 2 points mentioned above? The key is to meeting these 2 points lies in satisfying the intersection of R and S must not be emptied for any R belongs to RC and for any S from the SC. So obviously, when the configurations is equal to, when the configuration is a uniform configuration, the condition is naturally satisfied. And when the configuration is a joint configuration, the following relationship holds. These two relationship holds, and therefore, for any R belongs to RCI/CJ, it will exist an R1 that belongs to RCI, and also exist an R2 belongs to RCJ, satisfying that the R1 it's the satisfying the R equals to the R1 plus the R2. So similarly, that for every S belongs to the SCI/CJ, and it will exist the S1 and S2 satisfying this relationship. So since both the intersection of S1 and R1 is not emptied, and the intersection of S2 and R2 is not empty too, so it will follows that the intersections of S1 intersection of S and R is not empty also holds. So based on the definitions of the super quorum and from N commit and the recover, and we can derive two properties that P1 is any proposal that achieve fast commit on joint consensus, on joint configurations can be recovered on either uniform configuration CI or CJ. And the second is if a proposal P1 achieve fast commit on joint configuration CI/CJ and a proposal P2 achieve the fast commit on CJ/CK, then both P1 and P2 can be recovered on the CJ, which is the intersection of these two joint configurations. And finally, let's discuss over how does the leader use the recovery quorum and super quorum to address the safety issues in the recovery process. And we can use the C committed and the C effective to denote the configuration state of a node, where the C committed represent the configuration that the node knows that has been committed. For a leader, modifying the C committed means the leader knows that the corresponding log has been successfully appended to a quorum. And for a follower, modifying the configuration, the C committed means the follower knows that the leader has successfully appended the log corresponding to the configuration to a quorum. And the C effective represents the current effective configuration. Then, for example, the node has received and applied the configuration C, and when we execute a configuration change CI to C1 to C2, the configuration state machine of nodes in the cluster will undergo the following transactions. It will firstly be the CI, C1, and then to the C1 and the C1, C2, which means the C1 is already committed and the C1, C2 is effective configuration. And then the C1, C2 is committed in the cluster, and then it will switch to the C2 configuration. And finally, the C2 configuration has been committed. And we can also to draw a conclusion that the leader only needs to recover the first committed proposals under the intersections between the C committed and the C effective configuration. And obviously, when the C committed configuration, when the C committed is equal to the C effective, namely in 3 cases, like the C1, and these 3 cases, and we know that the L1/1 is evidently correct. And from the property P1 in the previous recovery quorum definition, this one, any proposal that achieve fast commit on CI/CJ can be recovered on either CI or CJ. And we know that in the cases C1 and C1, C2, regardless of whether fast commit is achieving using the C1 configuration or the C1, C2 configuration, which is less possible. For example, if a leader replicates this joint configuration C1, C2 to a superquorum of nodes, accept the fast commit afterward, and then, but hasn't broadcast the message that the C1, C2 has been committed to other nodes, both can be recovered using the C1 configuration. And similarly, the case C1, C2 and C2 can be recovered using the C2 configuration. So the following tables describe the corresponding relationships. When the new leader's configuration is C1, that the client can only use C1 to achieve the fast commit. So if in this stage, if a leader crashes, the new leader will pick the C1, which is the intersection of the C1 to recover. And in this stage, a client may use the C1 to achieve the fast commit, and the newly elected leader will use the C1 to recover the fast commit proposal, and after the C1, C2 is committed, then the client can use the C1, C2 to achieve fast commit. And in this stage, the new leader will also use the C1, C2 to recover. And if the new leader is switch its state machine, the state of its configuration state machine to C1, C2, and C2, then you can only use the C1, C2 to achieve the fast commit. And in these cases, the you can use the C1, C2 or C2 to achieve the fast commit. And in this case, if a leader crashes, and it will pick the C2 to recover the fast committed proposals. And same as the C2, and this is the same as this one. And we also have the transitional cases. That means the current configuration of the cluster is the joint configuration, like C1, C2. And in this case is similar with this one. And when the leader change its configuration from C1, C2 to C2, C3, and in these cases, the client can only use the C1, C2 or C2, C3 to achieve the fast commit. But whatever case, whatever the client used to achieve the fast commit, the newly elected leader will pick C2 to recovery. And as the proposal we mentioned above, that the C2 can successfully recover the fast commit proposals. And this and the other case is similar with this three. So I think we don't need to this 3-1 is similar with this 3-1. So this is the topics about the today's community meetings. And any questions?